Hello, good morning, students. So today we will discuss about one more topic with respect to earthquakes. In the last class, we have seen the introduction part of earthquake. So I will first start sharing the screen. I hope it is visible to you. So in the last class, we have discussed with respect to introduction of earthquake. So moving forward, we will discuss about what are the different earthquakes that took place in India. So all this we have seen in the previous class only. So now coming to the major earthquakes that hit our India during the past few decades. So it all started way back in the year 1897 when the first earthquake hit the Assam coast, and the death caused to the people was around 1500. The next earthquake that hit the Assam, once again, the earthquake took place in Assam in the 1950, and the amount of death recorded is 1526. Similarly, in the year 1993, although it is not in chronological order, it is as per the number of deaths. So, in the year 1993, in the Latur region, the earthquake occurred. Apart from that, in the year 1905, the earthquake occurred in the region Kangra, which is near the Himalayas, and the amount of death recorded was less than 20,000. Next earthquake that hit the earthquake in the India was in Gujarat. Around 20,000 people died. Kutch, Gujarat. This is remembered to us. We were used to be a student at that time. Another earthquake that hit the earth, India, is in the year 1934 in Bihar and Nepal. Less than 30,000 people were dead. Next, one more earthquake occurred in the year 2005 in the Jammu and Kashmir region, and the amount of death recorded were 130,000. Finally, the earthquake, which was the most severe, occurred in the year 2004 in the Indian Ocean, west coast of Sumatra, Indonesia. Less than 283,000 deaths were recorded. Now comes the question how to calculate the earthquake risk evaluation and mitigation. So evaluation already we have stated, that is how it is measured in terms of magnitude intensity by using seismograph. Mitigation of earthquake is of prime importance. Now we will see mitigation. Protecting against earthquake damage. Now, as we have seen that predicting an earthquake is highly impossible. But suppose an earthquake occurred, what is the amount of damage we can control? How we can protect against an earthquake, that we have to see. prepare a seismic risk map for the globe, which identifies rock types, liquefaction potential, landslide potential. This we need to understand. What we have to do, we have to prepare a seismic risk map for the globe, which identifies rock types, liquefaction potential, landslide potential. So what it means, that is, as you know, that different types of rocks are available, such as metamorphic rocks, igneous rock, sedimentary rocks. Different types of rocks are available. So what we are trying to do, we are trying to study the types of rock. How we are trying to study? By preparing a seismic risk map for the globe, which identifies the rock types and liquefaction potential and landslide potential. Apart from this, what we are trying to do? Extensive geological survey has to be done to identify all active faults, including hidden faults. Not only we have to calculate the amount of rocks present in that particular area, but also we have to calculate the amount of faults present, including hidden faults. Now, earthquake resistant design of structure. Enact building codes to design and building earthquake resistant structure in high seismic risk areas. Now, as we have seen that different types of zones are there, zone 2, 3, 4, 8, 5. So based on the severity of the zone, we need to establish or we need to construct earthquake resistant structures. So there are various codes available for IS design of earthquake resistant structures. We have to use them in a correct way, and we have to enact these building codes to design and build earthquake resistant structures in high seismic areas. Wood, steel, and reinforced concrete are preferred as they tend to move with the shaking ground. Unreinforced concrete and heavy masonry tend to move independently and in opposition to the shaking, battering one another until the structure collapse. See here, the most important point when we design earthquake resistant structure is which type of material we are using for preparation or construction of earthquake resistant structures. Wood, steel, and reinforced concrete. These three materials are preferred. Why? What is the reason? Because this tends to move with shaking ground. As the ground moves during an earthquake, these materials also tends to move. So by constructing our buildings with these materials help us to resist the collapse of a building during an earthquake. Now structural behavior under gravity loads and seismic loads. As you know that different types of loads are there. Wait 1 second. What I'm trying to do, we just mute the audio because it is me. It is wait. Hmm. Structural behavior under gravity and seismic loads. So what we are trying to do? Structural behavior we are trying to calculate. So gravity load one column, lateral load one column. So what is the difference? Direction of load is vertical in case of gravity load. If you see here, we are trying to compare the how a structure behaves under the application of gravity load and lateral load. What will happen is the direction of load will be vertical in case of gravity load, whereas the direction of the load will be horizontal in case of lateral load. Similarly, direction indirectly imposed on the structure. Gravity load is directly imposed on the structure, whereas lateral load is reversible in nature and cyclic. Next, deterministic load. Gravity load, maybe call it, we can consider it as a deterministic load that we can determine it. Whereas lateral load is not deterministic or not easy to estimate. How much is the amount of lateral load acting? We cannot estimate it. Do not, next coming gravity load, do not produce fatigue. Gravity load do not produce fatigue, whereas lateral load due to cyclic in nature produces fatigue. Fatigue meaning stress production due to cyclic load. As we are aware of that, fatigue is nothing but stress produced due to cyclic load. So lateral loads are more subjected to fatigue. Next, coming to gravity load, drift and deformation are small. So the drift and deformation are small if you consider the gravity load. Whereas drift and deformation are large. Structural shows inelastic behavior under seismic load. What we are trying to understand with respect to drift and deformation, in case of gravity load, the drift and deformation is very small. Whereas in case of lateral load, it is very large. Why it is large? The structure shows inelastic behavior under seismic loads. Due to the drift and deformations are large, what will happen is the structure will show inelastic behavior under seismic loads. Last but not the least, in flexural members, bending moment and central position is hogging and at end it is sagging. How is the load pattern in case of gravity load? In flexural members, bending moment and central position is hogging, that is negative, and it ends it is sagging, positive. In flexural members, alternative sagging and hogging moment occurs. In case of lateral load, what is happening? The flexural members alternatively sagging and hugging. So hugging and hogging movement both is occurring. Okay. Now two more differences are there under gravity load and lateral load. Shear force is small in comparison of seismic load. Shear force is small in comparison of seismic load, whereas shear force is large than gravity load. In case of gravity load, the shear force is very small. If you compare with the seismic load, the shear force is small, whereas in case of lateral load, the shear force is more. Lastly, in case of gravity load, the column subjected to axial force and less bending moments than seismic loading. The column is subjected to axial force. What is happening here is the column is subjected to axial force and less bending moment than seismic loading. Whereas here column is subjected to more shear force and building behave as cantilever. In case of lateral load, what is happening? The column is subjected to more shear force. As we have seen that the shear force is large in case of lateral load, the column is subjected to more shear force and building behave as cantilever. The tensile force act at side of seismic wave forces and opposite side there will be compression forces in the column. So this is the difference between gravity load and lateral load. If you see the figure also here, you can see that in case of gravity load, the shear force is less, whereas in case of lateral loading, the shear force is more. The bending moment and shear force also you can see the hogging and sagging pattern in case of gravity load and lateral load. See here. Now lateral load resisting structural system. As we are aware that we need to construct an earthquake resistant structure. Earthquake resistant structure means what? An structure that can withstand different types of loads during an earthquake. So for that we need to understand what are the lateral load resisting structural system, because the earthquake when it comes, lateral loads play a very important role. So there are basically three lateral load force resisting system. They are number one, moment resisting building frame system. Number two, shear wall or bearing wall system. Number three, dual system. So this we will see in detail. So what exactly is a moment resisting frame? It is nothing but a rectilinear assemblage of beams and columns with beams rigidly connected to the columns. So as you know that moment resisting frame is nothing but it is a combination of beams and columns. with beams rigidly connected to the columns. So the how they are connected, that is most important, because resistance to lateral force is provided primarily by rigid frame action. That is by the development of bending moment and shear force in the frame members and joints. What is happening is how the moment resisting frame is being established. It is established with the help of beams and columns, with beams rigidly connected to the column. This is a very important point. If they are flexible, then moment resisting frame cannot withstand the earthquake during an does not withstand the loads during an earthquake. By virtue of rigid beam column connections, a moment frame cannot displace laterally without bending the beams or columns depending on the geometry of the connection. So as we have seen that, as I have said you that why the beam column joint is rigid, what is the reason? Because by virtue of rigid beam column connection, a moment frame cannot displace laterally without bending the beams or columns. See here, this is very important. Once again, I'm trying to explain you. Just listen. What is happening is because the rigid beam column, because the beam column is a rigid one, what is happening is in case of a failure, this moment frame is not displacing laterally, as a result of which it is minimizing the loss during an earthquake. The bending rigidity and strength of the frame members is therefore the primary source of lateral stiffness and strength for the entire frame. So, what is playing an important factor? The bending rigidity and strength of frame members, that is beam column joint, because it is connected rigidly. This bending rigidity is the most important factor due to which the moment resisting frame is able to resist in moment. Now, this we can understand with the help of figure also. Moment resisting frames used for both structural steel and reinforced concrete structures. Not only for structural steel but also for reinforcement concrete construction also you can use moment resisting frame. The horizontal beams, once again, wait a second. The horizontal beams, just I will zoom it out. No, it is too much. Wait. Uh, the horizontal beams and vertical columns. How the beams are placed horizontally and columns are placed vertically. This provides both support for the structural weight and the strength and stiffness needed to resist lateral forces. So during an earthquake, lateral forces are most vulnerable. What they will do is they will shake the entire structure and the structure will collapse. So what this moment resisting frame is doing, the horizontal beams and vertical columns provide both support for the structure weight and strength and stiffness needed to. So these moment resisting frame is resisting the lateral force effect during an earthquake. The stiffness and strength are achieved through the use of rigid connection between the beams and columns. Once again, how the stiffness is provided to this moment resisting frame with the help of rigid beam column joints. Moment resisting frame systems are popular because they do not require braced frames. So these moment resisting frames are nowadays becoming popular because they do not require any braced frame. So as a result of which the cost of construction is also reduced. They do not require braced frames or structural walls, therefore permitting large open spaces and facets with many unobstructed window openings. So during a construction of a building, we are very much concerned about providing windows for ventilation and all. So this moment resisting frame, because it does not require any braced frame also, so the windows can be provided at any desired location. Now shear wall or bearing wall system. So it is also one type of moment resisting frame, shear wall or bearing wall system. Shear wall takes lateral loads placed on it by building itself. So as we have seen in case of moment resisting frame, the beams and columns are joined rigidly. So now shear walls, how they are able to resist the lateral loads? Their shear walls take lateral load placed on it by building itself, as well as lateral loads experience, if any, and when wind hits the structure and some instance earthquake. So shear walls, they are not connected rigidly with the help of columns, footings, they are not, they are separate. So what they are doing, how they are taking the load? They are taking the load by itself. Bearing walls are just that, bearing the weight of elements, beams, girders, building component attached to it. So as the name itself indicates, shear walls are also known as bearing walls. So whatever load are coming on it, it is bearing it without any connections. So if you can see here, this is your column, this is your slab, and this is your beam, and this is your RC shear wall. So this shear wall itself is taking all the loads without the help of any connections. Now, dual system. So till now what we have seen is moment resisting frame and next is shear wall. Now, dual system. So what is dual system? A dual system is a structural system in which an essentially complete frame provides support for gravity loads and resistance to lateral loads is provided by specially detailed moment resisting frame and shear walls or braced frame. So it is, as the name indicates, it is a dual system. So it is a combination of beams, column, as well as what you can say shear walls, bracing walls. So both shear walls and frames participate in resisting the lateral loads resisting from earthquakes or wind or storms. And the portion of these forces resisted by each one depends on its rigidity, modulus of elasticity, and ductility, and the possibility to develop plastic hinges in its parts. So what is the dual system and how it is helping in during an earthquake in able to resist the lateral loads? So it is a combination of moment resisting frame in which beams and columns are joined rigidly, and apart from that, it is a combination of shear wall or shear wall or bearing wall. So both shear walls and frames are participating in resisting the lateral loads resulting from earthquakes or due to any wind or any storm. So on what factor it depends? It depends on the rigidity, modulus of velocity, and its ductility, and the possibility to develop plastic hinges in its part. Because it is a combination of all the three, there is a possibility that plastic hinges are formed. So the moment resisting frame may be either steel or concrete, but concrete intermediate frames cannot be used in seismic zones 3 or 5. See, this dual resisting system, as we have seen that the moment resisting system may be a steel or concrete, but this type of dual system cannot be used in seismic zone 3 and 4, which is the most likely area which we can experience an earthquake. There we cannot use the steel or concrete moment resisting frame. The moment resisting frame must be capable of resisting at least 25% of the base shear, and the two systems must be designed to resist the lateral load in proportion to their relative rigidities. See here, we cannot predict an earthquake, but what we are trying to do, we are trying to minimize the damage caused by it. So what we are doing, we are trying to prepare a structure with the moment resisting frame with the help of which what we are doing, the lateral loads which are coming on the structure, we are minimizing it or we are resisting it by 25%. At least 25% of the damage we are trying to control. So if you see the figure, dual lateral load system, this is the wall frame dual system, this is the hole, this is the lateral frame, 25% lateral load minimum shear wall. This shear wall is preventing the lateral loads or the lateral loads which are coming due to storm or due to an earthquake. This shear wall or bearing wall is resisting all these loads. Now comes the question, what is the requirement of efficient earthquake resistance structural system? So till now what we have done is we have prepared a moment resisting frame dual. First we have studied about dual, sorry, moment resisting frame, which is a combination of beams and column which are joined rigidly. Secondly, we have studied about shear wall or bearing wall. Finally, we have studied about dual, which is a combination of both the two, and we have come to a conclusion that 25% of earthquake load can be minimized or lateral load can be minimized due to the construction of these lateral loads. Now, what are the requirements of an efficient earthquake resistant structural system? So, before going to that, we need to understand what is exactly is the What do you mean by earthquake resistance efficient earthquake resistant structural system? Earthquake resistant structural system means which is able to withstand maximum amount of lateral loads during an earthquake. As we have seen that 25% of earthquake load can be minimized by the construction of what you can say moment resisting frame, shear wall or bearing wall or DL system. Similarly, what best we can do to minimize the effect of earthquake? The building and its superstructure should be simple, symmetric, and regular in plan, and the elevation to prevent significant torsional forces. See here, the first important thing we need to keep in mind is how should be your building. The building and its superstructure should be very much simple. Simple in the sense how you can say the super building is simple. Nowadays we are preparing very aesthetic type of buildings. Lot of beams, columns are being what you can say adjusted as per our requirement. The symmetry is being affected. So if your building is in zone 3, 4, or 5, what we have to do? We have to keep the plan, section, and elevation very simple. Yes, there is a tendency that we can improve or we can provide a good elevation, but the symmetry is very important because how the beams and columns are being beam and column positioning is done, that is very much important. And apart from that, we have to keep into mind the effect of torsion forces because torsion forces are also plays a very important role during an earthquake. The building and its superstructure should have uniform and continuous distribution of mass, stiffness, strength, and ductility to avoid the overstressing of structural components due to stress concentration. See here. This is very important point. How the building and its superstructure should be. The building and its superstructure should have uniform and continuous distribution of mass. The building and superstructure should have uniform and continuous distribution of mass. It should not be that 5 kilonewton, what you can say, 500 kilonewton at one floor and 300 kilonewton another floor, at 800 kilonewton another floor. The building and its superstructure should have uniform and continuous distribution of mass. Apart from that, stiffness is a very important factor which we need to keep into mind. And the ductility, strength and ductility to avoid the overstressing of structural component. So what will happen is suppose there is uneven distribution of mass, stiffness, strength and ductility, there will be formation of stress concentration on the parts of an of a structure, beams, columns, and all, due to which your structure will become inefficient. So if you can see this figure, what is happening is this is the substructure, foundation, substructure, and this is your ground floor, second floor, and roof. So from the position to ground floor to roof, this is called your superstructure, and part beneath this is known as substructure. So if you see the figure only there, only you can realize that it is a uniform structure. The structure should have good lateral load resisting system and direct pathway without discontinuity. So this is also very important factor. What we are trying to do is, what we are trying to understand is, it looks so, damping devices is next. Hmm, 1 second. Okay, the structure should have good lateral load resisting system and direct pathway without discontinuity. Apart from that, integral action of soil foundation structural system. The different elements of the substructure and superstructure should be given connections together so that they can work as a single unit. See here, this is also very important part. What is that we are trying to say? Integral action of soil. Foundation superstructure, the different elements of the substructure and the superstructure should have rigidly connected together. So that manner in which the different connections are provided, it should be rigid. Then only it will be act as a single unit. The superstructure should be provided with compatible stiffness instant between its member connections supporting foundations. So this is understood easily. The superstructure should be detailed for adequate ductility so that elastic deformation can be controlled to develop plasticity. So as I said earlier also, there is a possibility of plastic in this formation. So the superstructure should be detailed for adequate ductility. The ductility of the structure should be good so that it can withstand deformation during plastic deformation. The structure should be able to dissipate seismic energy by yielding of its component. So when an earthquake occurs, what will happen is more amount of seismic energy is produced. So the element should be able to dissipate the seismic energy by yielding its component. The building should be light and should avoid unnecessary masses because the larger the mass, the more the seismic forces. See here, apart from providing a uniform mass, the building should be light as possible and should avoid unnecessary masses because if more mass is there then there will be more seismic forces, and more seismic forces means the most possibility of an earthquake. The superstructure should not have long cantilevers to avoid large deformation. See, the span of cantilever is also very much important. If it is a very large span, then there is chances of large deformation. So all these points are important, or what you can say, requirements of an efficient earthquake resisting system. So in the next class, we will discuss about damping devices. I hope you have understood. If you have any queries, you can just comment on the section. And if you have any problems or any associated any difficulties, you can just pin me a comment, and my email ID is also provided to you. Okay. So have a nice day. Thank you, friends.